Okay, we're going to get into chapter 14, and we're going to start as usual reviewing the objectives of this chapter. And to remind you, we're getting into the second of the three components of the cardiovascular system. You remember when we concluded Unit 3, we said the three components of the cardiovascular system include the heart, which we covered in Chapter 13, include also our blood vessels, which we're hitting here in Chapter 14, and then the blood, which we'll cover in Chapter 15. So we're still clearly in the cardiovascular system, looking at the blood vessels and the resulting pressure of the blood within them.
Were there review questions in 13?
Yes, there are chapter study guide questions for Chapter 13. They would be, did I upload them for this class? To say Chapter 13, Part 2.
And then you printed additional, like a Part 2?
Yes.
Or is there additional questions or just?
It'll say a Part 2 study guide.
Oh,
so that
we didn't get it. Yeah, I didn't see that one. Yeah, we only got this one, brief one and Part 1.
And it was not on the end of Part 2?
No.
May I look at it? Yeah, go ahead. Okay. There is a document. So, yes, there is one, parents, that exists, and clearly I have not.
On 13?
Yes. There is a. Yeah.
Maybe page 11. No.
So it's on the previous one.
There's two. There's a Part 1 study guide and there's a Part 2 study guide. I did not give you the Part 2. So thank you for bringing it to my attention. At the end of class, I'll upload that. Okay. Thank you. That does exist. All right. I'm sorry about that. That will be forthcoming. In Chapter 14, we'll talk about our different vessels, including the blood flow through them. We're going to talk about the role of pressure gradients. Right, all semester, we've been talking about gradients this, gradient that. So we're going to look at pressure gradients. Also talk about resistance and how those two correlate to the flow of blood throughout the body. We're going to review very quickly the anatomy of our arteries, arterioles, capillaries, venules, and veins, which we actually became introduced to last Thursday and kind of opened with this morning. We're then going to hone in on the arterioles, as identified. Not only are they the smallest of the arteries, but they're going to have our major contribution for changing resistance to the flow of blood and distribution of blood through the body. Right, so we'll look at the role of arterioles, and then if we have time, we'll talk about bulk flow, which we introduced this morning as well, across our capillaries. The abbreviation stands for what? ECF? Extracellular fluid. And then today, if we have time, we'll talk about mean arterial pressure, in addition to distributing blood through our organs, and then conclude the chapter with a reflex to changing our blood pressure. Right? So call back into practice all of our Unit 2 material, maintaining a reflex heart. We can apply it here in maintaining our blood pressure. So the first thing is to kind of keep it simple, and y'all got to envision in my brain, right? It's all about the, right, so Megan Trainor, it's all about, so no, we got to substitute the word though. It's all about the gradient. About that gradient, about that gradient. It's all about that gradient, keeping blood flowing. And we're going to look at specifically pressure gradients. It's all about pressure gradients, keeping blood flowing from one spot to another within the body. So how would blood flow in respect to a gradient?
Down.
It'll move down its gradient. So that implies from a higher pressure to a lower pressure. Blood flows down its pressure gradient from where the pressure is higher, or actually greatest, to where it's least. So this is going to be a bit more global than just across the cell membrane. We're looking at blood, a large volume of blood, so not like a tiny molecule across a membrane. But typically you would say it is active transport because we're using what to create the gradient? What is creating the gradient? What's creating the pressure gradient? The heart, which uses what? It acts as a pump that uses. If I want to pump, what does that muscle need? Energy, ATP. So by all technical definitions, sure, creating that pressure gradient is active process, but I wouldn't lump it into like we defined active transport. It's not just a specific molecule across a membrane. It really is an entire global process in the body, so it's big. No, it is active. I mean, we got to establish the gradient, but what I don't want you to confuse is just the flow of blood from point A to point B in your body is equating to a molecule across a membrane. Does that make sense where I'm trying to differentiate? But you're correct, it does take energy to create that gradient, just like we learned in active membrane transport. And the energy comes from the atria, the ventricles pumping and relaxing, etc. So there's definitely a pressure gradient that exists to keep the blood what? Flowing. If there is no gradient, there's no flow, and then, or really quick, right? You're on the way to death. 6 feet under it. Something bad is going on. And so we've got to just keep in the back of our mind that pressure gradient exists to keep the blood going, flowing from one spot to another. And the way that gradient is established is not only using the heart, but also our blood vessels. And we summarized this image on Thursday a little bit, so I won't overdo it, if you will. But let's just review. Vessels on the left are arteries. On the right, we have veins, intermediate. In the very middle, we have capillaries. And then leading between the artery and the capillaries are vessels called arterioles. And so we have two arterioles shown here. One has an arrow pointing to it, and another here. So those are arterioles. But you can see the diameter of the vessel significantly smaller, hopefully. Arterioles take blood to our capillaries, where which process occurs? Exchange. You could say bulk flow, right? And there is an exchange. The two phases of bulk flow, if we're pushing something out, would be filtration. So let's just put it back on here. You probably put it in your handout last week, which is great. So last week we drew on this little vessel, right? We said if filtrate, hormones, whatever is being pushed out, that process is called filtration. Pressure is forcing solutes, stuff, blood plasma out to the what?
Whatever needs it.
Whatever needs it. So in the interstitial fluid, into whatever. It could be a muscle, it could be the brain, liver, fill in the blank, right? Some part of the body. Conversely, we can also upload, if you will, products, and those are called. You can call it reabsorption or absorption. Both are acceptable. Question? Go ahead, Henry. Question? So the capillaries, you guys are right, collectively do carry out bulk flow. But if we were to really pick it apart, we said that's where filtration happens, forcing plasma to the what? Interstitial fluid. And then also, if the pressure gradient reverses, the interstitial fluid can be taken back into the plasma by a process called reabsorption or absorption. Fluid that remains trapped in a capillary would then enter into different types of, what's next? Venules first. So I have one highlighted here, and the one below it could be labeled just as well. What's happening to the diameter of the blood vessels now? Between the capillary and the venules. It's getting bigger. And then the blood would drain into our veins, where the lumen is the largest, right? It's even greater than the largest. Which carry blood back to the heart. The amount of oxygen, probably lower if you're in the systemic circuit, but Depends if you're holding your breath or hyperventilation, whatever, right, the case may be. But generally, right, under normal conditions, it would have a lower proportion of oxygen. And maybe a higher proportion of which gas? Carbon dioxide. Also noted in the textbook is the presence of connective tissue. You'll find it around each of your arteries, veins, arterioles, and venules, but we do not find it around the what? Capillaries. There is no definitive, like, thick connective tissue layer around your capillaries. Why is this thick connective tissue layer absent in the capillaries?
So we can filter or absorb stuff.
So it can filter and reabsorb. If there's this big thick layer there, it's going to be severely hindered if probably wouldn't even happen at all, to be honest. Which is why you wouldn't find it an artery or vein. So connective tissue. Now, why is connective tissue present in our other vessels?
So it doesn't leak out.
It may have prevent leaking. What else? So it can stretch as well and not do what? Rip apart. So your arteries and your veins, arterioles, venules can stretch when blood enters them, but hopefully not rupture. So we need that connective tissue to connect it and hold it together. So although it does prevent any passage of materials, its primary role is to just prevent those tissues from ripping apart. Look at the density of the connective tissue between the venous, right, the veins and the arteries. Is there any difference? It's a little bit thinner in the veins and a little bit thicker in the arteries. You notice the thickness of the connective tissue here versus here. Can you see the difference? It's a little bit thicker in the arteries. So what can we take away? Well, it's present in both, but it's a little bit thicker in the arteries, so they're more elastic. Then the arteries do have more pressure. Because where do we feel our pulse? Arteries. So we know that the arteries have to stretch, recoil, stretch, recoil, stretch, recoil with each stroke volume. Remember we're using the word, chapter 13, stroke volume? So each stroke volume that enters into your arterial system, stretch pulses. And so we want those arteries to be very, the term is elastic. Are venules elastic? Yes, but not as much. We certainly don't want them to just bust either. We don't want any of our vessels to bust. We see some smooth musculature as well in the arteries, arterioles, sometimes in the veins, and certainly, or sometimes in the venules, but definitely in the veins as well. Why might we need smooth muscles? To what?
Squeeze it down.
To squeeze or even relax. Okay, so squeezing would be contraction, and relaxation. And so we can change the what? If I squeeze or open, pressure, and more directly, that'd be kind of indirect to the what? If I squeeze or open, I'm changing directly the lumen diameter, which influences the volume which it can hold, which influences the pressure. But the muscles directly just change the diameter, open or close, big or small.
It changes the lumen diameter, which changes what?
So just put the changes the lumen diameter. Okay. And what we're explaining is when you change that diameter, that influences the volume, which the blood can occupy, which we know can also influence the pressure. So we identify that change in diameter directly influences the volume of blood that can be held there, which influences the pressure of the blood in that muscle. Does that answer?
Yes. Thank you.
We can see some thickness differences between the arteries and the veins here, though, in that smooth musculature. What's different? You see a more thick muscle mass in the artery than you do in the vein. You see it's a little bit thicker, artery versus the vein. And so, takeaway is?
Artery does more.
The arteries could change more. Could change the diameter and the contractility. So the arteries can change their diameter a bit more forcefully, I guess, than say a vein could. A vein can, but not near to the degree that an artery could. You'll also find smooth musculature in the arterioles. We'll talk about these have a huge impact on the flow of blood to where? Capillaries. Arterioles. May want to put a big star because the arterioles are going to kind of be our star of distribution for blood on your little arteriole, excuse me, the little star. What happens here is going to really impact what happens in the capillaries. Do our capillaries have any smooth musculature? They don't, so they can't what? They can't constrict nor relax, dilate. So they are dependent again upon the pressure in the arterioles, the flow coming down from the arterioles. What other questions do you have about some of these structural features that we see between the arteries versus veins, venules, capillaries, arterioles, blood flow? Okay. We really kind of discussed a bit of the structural characteristics in that image which we summarized, so I'll refer you to figure 14.6, and may have already kind of written some of your notes on the other side, but figure 14.6 backed up what we just talked about, but put numbers to it. So it quantitates the thickness of the smooth musculature, the overall thickness of the entire thing, and then some primary structures, features, excuse me, about those. Again, we noted that the diameter is greatest in which vessel? The veins, but still big in the arteries. Arteries and veins are still thick, but most thick are the arteries. And then we also noted that the capillaries are going to be our thinnest structures, smallest lumen. And we also noted that arterioles have smooth muscles. Venules may have some smooth muscle, depending on where they're at. What questions do you have about some of these structures and functions of these different vessels? Or are you able to correlate that to what we just took notes on the image? You're okay with that? Any questions? General. I will not say what is 0.4, whatever. Okay, so as long as you acknowledge the things which we've talked about, without quantitating is important, but concepts are probably more important at this point. Good. Additional questions? And so here we are talking about our blood vessels, and what's happening in them is they're distributing blood. And so up till now you probably used the term blood flow. I want to introduce maybe a new term to you is perfusion. You can equate these two can be synonymous to you. So if I say perfusion, tissue perfusion, that tells me blood flow in a tissue. So I want you to equate that because we're going to use this term in the respiratory system. If I talk about ventilation, perfusion, coupling, I'm just giving an example. Ventilation means what? breathing. Perfusion means blood flow. Ventilation, perfusion, coupling.
So the process of blood flow.
Oh, mixing both.
That's,
It's gain oxygen from lungs.
Blood and lung.
they're working together.
Yeah.
You're coupling. You're matching what? Blood flow and airflow. Ventilation, perfusion, coupling. It's matching airflow with blood flow. Or I could say blood flow, I could have said blood flow, I could have said perfusion was the point of that example. So if I say perfusion, I'm saying also blood flow. And the blood flow or the perfusion into an organ is dependent upon two primary factors. They include resistance and pressure. What about resistance? What does that word imply?
It's restraint.
Restraint, what else could we say? Pushback, opposition, or hindrance, or something like that. So at face value, it doesn't make sense. Why are there some kind of pushback or something like that in the body? And there are pushbacks, resistance factors in the body. There are three primary resistance factors that we will cover coming up in a minute. Maybe you can just say there are three primary. We'll elaborate them in a minute, in a few minutes. There are three major types of resistance factors to the distribution or the perfusion of blood into an organ. But if there's a resistance factor, the blood flow would be,
If there was what?
if there's resistance, the blood flow to that organ is less. Okay, so let's at least acknowledge resistance has an inverse relationship with blood flow. There's an inverse relationship between resistance and perfusion or blood flow. Inverse means opposite. So if there's a lot of resistance, the blood flow is less. If there's not so much resistance, the blood flow is elevated. So resistance factors influence the distribution of blood through the body. But also, critical for the distribution of blood is the pressure gradients, the blood pressure gradients. What do you think the relationship is between the blood pressure gradient and perfusion? Direct. The higher the pressure, the blood flow is more, fast, greater, more enhanced. There's a direct relationship between the pressure gradient and the flow of blood into a particular organ. Again, so if we want to see if blood's going to an organ, we've got to look at it if there's any resistance to the flow of blood and if the level of the gradients. So you can even look at it if you're working in a hospital and you got a patient coming in and they're complaining of chest pain. So like, was there any resistance factor like a clot in the blood or something like that, or heart's not working and there's no gradient, right? It applies to somebody who's healthy as well. So look at the distribution of blood to an organ. We could quantitate it. Again, this is going to be something that I'm not going to have you calculate, but I just want you to see this formula. In this formula, it summarizes what we just mentioned. The F stands for what? Flow. And if we work across, since it's on top of the formula, is directly proportionate to the what? What does this stand for? The change in pressure. Okay, so the flow of blood is directly related to the pressure gradient. Yet, what about resistance? Inversely related to resistance. So that formula really just concisely summarizes what took us a couple of minutes to illustrate. If my resistance goes up, my blood flow goes down. If my pressure gradient goes up, my blood flow goes up. We okay on that relationship? Again, we'll come back to the resistance factors, and then review the pressure gradient that exists in our systemic circuit. Before we look at those factors, I want to look at the arterioles and our arteries, really. Figure 14.7 does a nice job to help visualize what's happening when blood enters in the systemic circuit. If you remember, the left ventricle has to propel that stroke volume at a high enough pressure to not only get out of the heart, but to get out of the heart and then, say, to the bottom of your toes and then back to the heart. And so it has to have a really huge pressure gradient to propel that blood. And so this image helps illustrate that the arteries and arterioles stretch with each stroke volume, and this is where you could pick up your what? What can I measure here? My pulse. Okay. And so we can see a nice huge pressure, right, fluctuation in the arteries and the arterioles. We had a question yesterday in the Monday class about these. Do our arteries have valves?
No.
No. This is just showing a cross-section of blood coming from the left ventricle, just simplified, and the aortic valve, which leads out to the systemic circuit. So this valve is not in an artery. It's not representing that you find, but it is the aortic valve that separates the left ventricular blood with the systemic blood. Okay. But the big thing is, can you see how this vessel stretches? That should tie back into what we studied last week about the afterload, that stroke volume, that blood vessel stretches, and that gives back pressure. But hopefully it continues to go away from the heart, away from the left ventricle. Does this image bring up any questions? Okay, so our pressure is fluctuating. We'll elaborate that more. And if we turn our attention to figure 14.15 in your textbook, this is going to correlate two things. Again, non-action potentials, okay? And this is plotting two things to hopefully illustrate the relationship. The first plot is looking at what? What is that? Cross-sectional area, right? How much surface area a particular vessel might occupy. And then below that, it's correlating it to what? Velocity, which is another word for speed. Okay. We're correlating the surface area of a vessel to the speed of the blood through those particular vessels. Okay. First thing is, what might stand out about the relationship between surface area and velocity? They're inverse. The greater the surface area, the velocity is lower. Smaller the surface area, the higher the velocity, the greater the velocity. So we should be able to hopefully take away this inverse relationship between surface area and velocity of blood through a particular vessel. We're going to look at the different vessels, starting out with the aorta. The aorta is going to have, you only have one aorta, contrast to all the blood vessels in your body, right? And so surface area-wise, it's going to be very minimal, contrasted to all of our other vessels. Even though the diameter of the aorta is the largest, it doesn't take up a lot of space in your body. Okay? So its cross-sectional area is minimal. And the blood velocity is the highest and the greatest in the body, right? This is going to be the greatest amount of velocity of blood traveling through the body as it exits the left ventricle and gets propelled out into the systemic circuit. Aorta, branching off of it, will be individual what? Arteries. Where our diameter gets to become smaller, but our number of vessels increase. So our cross-sectional area is beginning to rise a little bit, and the velocity would begin to decrease a little bit. Next in line would be the arteriole. My animation got off a little bit, but the next in line would be the arterioles. I'm gonna back up the animation though, so you can see the plot. My animation came off a little bit. Next in line would be the arterioles. I want you to notice here, the cross-sectional area. What happens at the arterioles? It transitions significantly. Can you see that huge, right? So we went from about 1,000 up to almost 3,000 cubic centimeters. And so nearly threefold. Does that make sense? If we saw this almost threefold increase in surface area, what do you expect to see in the velocity? Decrease profoundly. Okay? So we see a sharp increase in surface cross-sectional area and then a respective sharp decline in the speed of blood through the arterioles. So blood flow plummets as it exits the arterioles.
I'm a little confused. What do you mean by cross-section?
The
arterioles are smaller than arteries.
Right, and so we're talking about total kind of surface area. If I were to take a sample of a tissue in the body, if I were to just slice it, what would I find most of?
Oh, long.
Not long, cross. Right, so let's say we're chop right here.
Yeah.
Right through my biceps, I would see more of what?
You have more arterioles than you have arteries, is what you're saying.
Yes,
Yeah.
surface area. And then I would have even more what? Capillaries. Because the capillaries are the ones that do the exchange. So to help you with this, a lot of times I kind of go with a non-biology reference. Okay, so let's think about your little hometown, wherever you're from. Okay, and let's say you're like from my hometown and you're far away from the main artery, the interstate, right? Okay, and then which is even branching off from the main artery, the interstate would be your state highway, the arterioles, right? And then branching off of the state highways, you would have maybe city streets, so your little arterioles. Which is going to have more surface area? Okay. One highway cutting through your town, or all the city streets making up your town. The city streets. In this analogy, the city streets would be analogous to the capillaries. So they're going to take up more surface area. However, to get to and fro, we need to kind of speed the flow up, the flow of traffic, or the flow of blood in our body, right? And so we'd have state highways leading there, or we'd have arterioles. To even get to those arterioles and state highways, we have something bigger, like an aorta, for example. And so even though the highway is larger than a city street, they each are going to have a unique purpose. And the distribution of cars, the distribution of blood, the speed is different because the size of the vessels is different, because the size of the city streets are different. Okay? So they serve a similar capacity in transport, but because the way they're made, they don't transport at the same rate. Does that make a bit of sense a little bit? Okay. And so if I were to take a cross-section of a town, there might be a tiny little section of the highway, there might be a whole bunch of city streets. If I were to take a cross-section of my tissue, I'd have a few arteries, but a whole lot of capillaries. Does that make sense? Hopefully. I don't know. And so by the time we get down to the capillaries, excuse me, let me back up, the arterioles, which drain off of the arteries, we noted a significant increase in surface area. Okay? But I want you to highlight right here. Notice that, yes, the velocity drops, but it does what? What's another word? It bottoms out. It plummets. We see the greatest drop in velocity at which vessels? Arterioles. Very good. What was just noted, this is because the capillaries can't control what's going on. And so we need to bottom out that velocity so that the capillaries can do what? Filter in, reabsorb. Slow that blood down so the capillaries can do their job. Filter out the blood, reabsorb interstitial fluid. And correspondingly, the surface area of our capillaries is what? The greatest. Are we doing okay? So our arterioles, this increase in surface area causes a plummet in the speed of blood so that it's nice and slow by the time it gets to the capillaries. And then something cool happens is when the capillaries, as you noted, drain into the venules, we have fewer venules. The diameter goes a little back up a little bit. So what's So our surface area goes, total cross-sectional surface area goes down for our venules. What's happening to the speed of blood? It's starting to pick back up. So once your blood flow goes to the capillaries, just because it's very minimal at the capillaries, doesn't mean it's going to stay minimal forever. Okay? Once we open up and let the blood go back into the venules, our speed picks up. And then we can drain into the veins. If we look at cross-sectional wise, looks pretty similar to, say, our arteries. But do we ever recover? We pick up, but we don't ever recover that initial speed. Why don't we ever see a full recovery of the initial speed?
It's not it's further away from the heart, and we're trying to get back up.
Because it's further away from the heart, and we just kind of squeeze shoot it right here, right? So even though we have enough pressure pushing it, we're not going to be able to regain that full velocity. But we're going to be able to pick it up, some, just not fully. Does that make a little bit of sense? And then by the time we get to the vena cava, flowing in there pretty nice. So hopefully you should be able to make a connection between the cross-sectional area and the velocity. The relationship is what? Inverse. The greatest change in velocity happens across the arterioles because they're regulating blood flow into the capillaries. Yet the speed picks up once blood gets into the what? The venules. We also mentioned we're going to identify the pressure gradient that helps the distribution of blood. We're going to use what's called the mean arterial pressure. You should recall that from your lab a few weeks ago, about what, 3 weeks? 3 weeks ago we talked about the mean arterial pressure, which is the kind of average blood pressure, taking into consideration the systolic and the diastolic pressure. And so if we're to look at the pressure gradients, where is the pressure going to be the greatest? In the aorta as it exits the left ventricle. So if we're looking at the systemic circuit, even comparing it to the pulmonary circuit, your greatest pressure is going to be as blood exits that left ventricle and gets pushed out into the aorta. And so the average mean arterial pressure is about 85 millimeters of mercury. We know it's going to have a higher systolic and a lower diastolic, but the average is about 85 mean arterial pressure. What happens to the pressure as it travels through the body? It drops. Will we see it go back up like velocity?
A little bit.
I'll give you another shot.
I mean, once it gets to the, you just said, once it gets to the venules.
Don't confuse speed with pressure.
What did you ask?
Does the pressure pick back up after it's been through the system? It does, and it actually continues to decline throughout the system because we need a gradient to keep it flowing. Okay? And so it continues to decline. At the capillaries, the pressure is low, but it's not the least in the body. We still need it to be lower in the venules, than in the veins. And so that by the time the blood returns to the right atrium, our blood pressure is pretty close to 0 millimeters of mercury. Very low. Vena cava is just opening, draining into the right atrium. So what is the gradient then? The blood does flow from high to low. What is numerically, if we're using these values, what's the gradient? How many millimeters of mercury? Keep blood going from the left ventricle to the right atrium. 85. 85 minus 0 is 85. So it's a huge pressure gradient. Pushing blood from the left ventricle, returning it over to the right atrium. The pressure gradients of about 85 mean arterial pressure keeps blood flowing. It continues to decline throughout the system. Any questions before we look at the changes that happen in the actual vessels? We turn to figure 14.3 in your textbook. Same type of layouts. In the purple is plotted the systemic circuit, and in the green, the pulmonary circuit. We've been kind of honing in on the systemic circuit that distributes blood to our body. And so the same kind of alignment which we've seen, and again, my animation's off a little bit for the capillaries and the arterioles. But at our arteries, and most notably at the aorta, the blood pressure is the greatest. And after the arteries, blood goes into our arterioles. What happens here? Pressure drops, and again, the blood. We go from here to here. We see, and then here. It decreases the most. Can you see the most significant drop in pressure happens in the arterioles? Because they're trying to control what happens in the capillaries. Where we still need enough pressure, but not so high. So the arterioles not only drop the velocity, but they also drop the pressure of the blood. So it's ready to go at the capillaries.
What's the green line?
The green line is the pulmonary circuit. So you'll also see a pressure gradient, but before we get there, I want to acknowledge the systemic circuit. So the capillaries, do they exhibit blood pressure? Is there measurable blood pressure in your capillaries? Yes. If there is no pressure, there is no flow. Yeah, there's no gradients, and there's no flow. So there is blood pressure in the capillaries. It's higher as blood enters and lower as blood exits, but it's never at 0. So we still see a decline in pressure, but not near to this degree that we saw in the arterioles. And pointing this out here, maybe you want to, it might be useful to label here. When the pressure is highest as blood enters the capillaries, what process is going to happen? Which one? Filtration. Filtration happens here, and the pressure drops a little bit. We can see more reabsorption of the capillaries. So it might be good to label here filtration happens, and here reabsorption happens.
With the veins at the very end of the system not having any pressure. What's up with the valves? Over there, 3 and 4?
I'm going to repeat that in just a second. Oh. So our pressure continues to decline. By the time blood gets into our venules, the pressure is still very low. But by the time it gets to our veins and our vena cava, we're approaching which value? About 0 millimeters of mercury. But we still have a gradient pushing the blood from out of the aorta back into all of our veins, trying to keep it returning to the right side of the heart. What was just noted then, it's like, well, if veins, blood pressure is so low, how do they get blood back? And the question was that the job of the valves? And the answer is yes. Veins have valves because the pressure is so low, we don't want the blood to kind of drain back and pool. And so this helps the blood get back. Good job.
So the valves become
Kinda. Question was, or note was like, are they kind of like a ladder? Sure. And better described as gates. Okay. That's what they are. They just open and close. But remember, they're just like in your heart. They're connective tissue, so they're not muscles. Just pressure opens them and closes them. So, yeah, little pressure gates. Open and close. I'm trying to think of a visual analogy which you might have experienced.
I keep thinking of like fish ladders on a man-made dam, but that's not really the same.
I was trying to think, I haven't been to too many water parks here, but I was trying to think if you want like a lazy river or something, and if they do have sometimes little gates you can go through and keep you going this way, right? So it'd be kind of like a little gate like that. Going this way, not that way.
Kind of like a subway turnstile.
Kind of like a subway turnstile.
I don't know what that is.
It's a one-way gate. You explained it properly.
They're just ladders that fish can go up over the dam so they can continue their migration path.
They just can't go backwards.
Salmon.
Kind of.
So valves and veins do what? What do valves and veins do? Prevent the blood from going backwards, because what would be opposing that blood getting back to the heart? Pressure's low. Even though the speed's kind of picking up a little bit, the pressure's low. When you stand up or whatever, the probability of blood just collecting in your tissues is high. So we throw some veins in there, or excuse me, valves in your veins, and it's pushed up. And we'll come back to the veins and talk about that. But as identified, we were looking predominantly at the systemic circuit, but we could also note that the pulmonary circuit exhibits as well a pressure gradient to keep blood going from the right ventricle back over to the left atrium. However, the gradient is significantly what? Lower. The pressure gradient, it exists, but it's significantly less in the pulmonary circuit. This will tie right back into what we studied in chapter 13. The left ventricle is thicker than the right ventricle, because the right ventricle doesn't have to generate as much what? Pressure. Okay. It's only pushing blood, as described as next door to the lungs. It doesn't have to generate near the force. It doesn't have near the amount of resistance that the systemic circuit has. There's still a pressure gradient that exists. Are you able to see this decline in pressure throughout the systemic circuit? Hopefully. We can see another value, not looking at the mean arterial pressure, but just direct measurements. So looking a little bit more specific, the plotting of the pressure is in the purple. And so, again, the same layout. So first we have the arteries. These are aorta, arteries. How could we describe the pressure in the arteries? How could you describe pressure in the arteries?
Pretty high.
It's high then. What's it doing?
Oh, there. Is that the heartbeat?
It's fluctuating.
It's fluctuating, or we would say it is
Sine wave.
pulsing. The blood pressure is pulsatile in our arteries, because you can measure your pulse. It is pulsatile between your, what would this greatest pressure be, your systolic pressure, and then this would be the diastolic pressure. Did I hear it? Yes.
Okay.
Just like in lab. The big number is systolic when the ventricle is contracting. The low number is when the ventricle is in diastole and relaxing. And you could take that other map and overlay it and plot the mean arterial pressure through it if you really wanted to.
You said diastolic is contracting.
No. Well, systolic is contracting. Diastolic is the ventricle is relaxing. So with each heartbeat, each stroke volume that's propelled out, we see a nice little pressure change. We can measure it in the arteries. We would measure that as either your blood pressure, or you could count it by measuring your pulse. So you would describe the flow of blood through the arteries as being pulsatile. That makes some sense? You see that fluctuating? How would you describe it in the arterioles? It's definitely declining. We said the most significant drop in pressure happens here, but it is also pulsatile. So arterial blood flow is pulsatile as well, but as noted, it does decline throughout the system. I want to make a modification to this image. If you really scrutinize it, right? It looks like blood enters the capillaries as being very pulsatile. And from what I understand, that's not a good thing. And so I want you to straighten out your line so that it exits the arterioles nice and steady and enters the capillaries. Sort of straighten out that pulsing at the end of the arterioles.
It shouldn't be in the capillary.
Right. Well, we don't want the capillaries
Bust the
stretching. We
capillaries.
don't want to bust the capillaries. It's that changing might risk busting them. Rupturing.
They don't have the connective tissue.
They don't have that outer connective tissue, protective connective tissue. But we still need enough pressure to filter and absorb. A term that you can use to describe this no longer pulsatile blood flow is called laminar. Your book uses the word constant. So I could say the blood flow is laminar in the capillaries and in the venules and in the veins, and it's while it's what in the arteries? Pulsatile. So we'll use the word laminar. You usually see that with like airflow, but it's anything you can talk about in fluid dynamics. Okay, so nice and steady, like constant, not turbulent, not fluctuating. So again, by the time the blood enters the capillaries, we transition over to a laminar flow, stays steady, or laminar in the venules and in the veins. Any questions before I move on to identify those three resistance factors? If we go ahead and identify the factors that resist the flow of blood, three things, including viscosity, blood vessel length, and blood vessel diameter. I'll elaborate on each of these in just a moment. Again, blood viscosity, blood vessel length, and blood vessel diameter influence the resistance of blood flow throughout the body. What does viscosity mean? How thick it is. What do you think the relationship is between viscosity and the flow of blood?
Thicker will flow as well.
There's things in there like proteins and sugars and hormones, neurotransmitter, water cells. And so if a blood becomes more viscous, the resistance is higher. And we said resistance opposes blood flow. So the more thick the blood is, the more resistance, so the flow is. What might cause your blood to become too viscous? What? In the blood? Okay, so like excessive nutrients, like excessive cholesterol. Very good. What else might cause? Another one you might be most familiar with is too much sugar. Diabetes, for example, causes blood to become too viscous. What other like non-disease scenario might cause you to have blood? Hydration. So which state? Dehydration. So I'm just not drinking enough water.
Doesn't temperature have something to do with it too? Like if you're cold or something?
I would think it could have some, but
more like extreme cold hypothermia.
so certainly hypothermia, your blood would become, it would chill and become kind of gelatinous, which would be dead before it gets to that point. Yeah, if you have excessive sodium, or you just don't drink water, for example. Or maybe you don't drink water and you donate to the OBI or the Red Cross in your blood. And all kinds of stuff going on.
Do you know anything about blood becoming, as they say, thinner?
Yeah, certainly.
Hot climate, like Arizona? That's what
So it's kind of you're doing the opposite of what was asked a moment ago. Like could cold make it too viscous, and could hot make it a little bit less viscous. Thank you. So more thin. I would think there's going to be some correlation, a little bit, but the magnitude, I don't know if it's enough to have like a major impact. Okay? I mean, at some point you're going to get so hot or so cold that that's not your issue. The blood distribution, the extreme temperatures damaging your tissues. But certainly, your blood viscosity from any moment to moment shouldn't change. Like if I were to measure your viscosity now, and then now, and now, right? That'd be pretty constant, right? Surely from day to day or week to week, and definitely year to year, it's going to vary. But right, from moment to moment, it's not going to fluctuate quickly. And so although viscosity is a form of resistance, working in the background, ever present, it's not going to have a major implication for blood flow. Because it's constant at any given moment. Likewise, so that kind of description is your blood vessel length. Your blood vessels, once you reach adulthood, are formed, right? There are rare circumstances if you have a traumatic injury or a baby, right, getting more blood vessels or something. But taking those extremes away, your blood vessels, right, are normal, like same length. So even though the blood vessel length is constant, it does contribute to the resistance of blood and how it gets throughout the body. What do you think the correlation is between the length of a blood vessel and the longer blood vessels have more resistance? You can put this into practice. Your blood vessels are longer in which circuit? The systemic circuit. There's a lot more resistance in the systemic circuit. Heart has, left side of the heart has to rate more pressure, etc. But you know, once you're developed, it's pretty constant. So it's there. The body's got to account for it. What does change from moment to moment to moment to moment is the diameter of your blood vessels, because you noted earlier the presence of the smooth muscles in there, and most specifically your arterioles. We can change those blood vessel diameters the most often. So our greatest source of resistance factors comes from the diameter of our blood vessels. Which state causes more resistance? A blood vessel that is what? Constricted or smaller. So if a blood vessel is diameter is the lumen is smaller, the resistance is elevated, and our blood flow is less. So if I want less blood flow to go to, say, my liver, because I'm not exercising, right, I'm taking a nap, my arterioles would constrict. And if I begin to exercise, say, the arterioles to my skeletal muscles would begin to open up, dilate, relax. Very good. And so let's just review those terminology real quick.
So the first two would be directly related, and then the diameter would
Let me back up. All of these are types of resistance factors.
Right.
If something about them increases, the blood flow would decrease.
Oh, okay.
If our blood becomes so viscous, too excessively viscous, the blood flow goes down.
Mhm.
If our blood vessels become excessively long, the blood flow distribution is less. If our blood vessel diameter becomes so small, the resistance is so high, and the blood flow would be less. And so let's conclude with these terms. Visualizing what you guys identified a moment ago. If we look at an arteriole in the first panel, under normal status, you look at the diameter of its lumen, it could also constrict. Okay? It's called a vasoconstriction. What happens to the lumen? Much smaller. Our resistance goes up, and the blood flow to the organ downstream is less. Conversely, if an organ becomes more metabolically active, we might see the vessels do what? What term could we use? Vasodilation. Vasodilate. So vaso, vessel, dilation. our resistance goes down and our blood flow goes up. We'll conclude our discussion here, and then we'll review our Unit 3 exams.